My name's Harriet. I hack your AI so the bad guys can't. Hello everyone, welcome back to episode 3 of this Intro to AI Security series. This episode is all about real AI attacks, and just to clarify, it's not about using AI to create attacks, but it's about attacking the AI itself. So like I said, I worked for 6 years at the intersection of data science and cybersecurity before I started my PhD in machine learning security and learned all about the different ways that you can hack AI. And I was really surprised by the lack of conversation around it, and it was of course a very different time. But the most common question I get is still, is the AI threat real? Like, is this just an academic threat, or could this actually harm real productionized systems? And my answer to this is yes, the threat is absolutely real. And just because you're not seeing headlines about AI attacks every second day doesn't mean that you shouldn't prepare for when this could happen. I mean, if we think about the adoption and rise of the internet in the latter half of the 20th century and how massive the cybersecurity threat is today, there's no way that you would travel back in time and tell someone in the 1970s that they shouldn't care about cybersecurity. And to me, it's the same in AI security. Maybe we're not seeing big, high-profile attacks in the media now, but one day we could be, especially if we continue at this current trajectory. And I talk about AI security a lot at conferences, at keynotes, trainings as part of my job. I always get someone come up after every talk to tell me about some sort of AI incident that happened at their organization. And the reason that we're not seeing these kinds of attacks in the newspapers or on TikTok is because, first of all, there's not really a common lexicon that people would use to refer to these kinds of incidents. There really isn't that technical and policy ecosystem and the tools to support just communication about these kinds of attacks when they do happen in the wild. I've mentioned before that there are over 100 different kinds of offensive AI techniques that can be employed, and many of these aren't necessarily realistic for the real world quite yet, but they have been proven to work in academic and controlled environments. So to me, surely we should be ensuring that our productionized systems are also secure and immune to those kinds of attacks. Because just because it's been proven to work in a controlled environment doesn't necessarily mean that that's where it's going to stay. And we at least have the field of cybersecurity to point to as a beacon that can lead the way in looking at what kinds of emerging threats are realistic and which kinds aren't. Now, when I talk about adversarial machine learning and explain what kinds of attacks are encompassed within this field, I usually like to refer to the machine learning life cycle. The machine learning life cycle is a high-level overview of how a data scientist would build a model, but it is also a way of describing the ML attack surface. You could broadly lump the kinds of attacks into 4 buckets. You have poisoning attacks, which is poisoning training data so the model learns the wrong thing. You have extraction attacks, where you're creating a near replica of the model to train and launch further attacks. You have evasion attacks, where you're causing prediction or classification to be incorrect. And you have inference attacks. And so recently I've discovered that instead of referring to attacks in terms of where in the attack surface they happen, like this is a very technical practitioner point of view, in this episode I'm going to be talking through the attacks in terms of the ways that they actually impact the model or the AI system. And in general, attacks on AI systems fall under 3 categories: disrupt, deceive, or disclose. Disrupt is when you're causing the model to malfunction or break in some way. Deceive is when, in a targeted way, you're causing the AI system to misinterpret its surroundings. And disclose is when you're causing the model to leak information that it is not meant to. So let's start with disrupt. Disrupting the model causes the model to break or malfunction in some way. Whether this means that it is not able to perform as intended or it can't work at all, You could consider this like the DDoS attack in cyber and information security. A DDoS attack is a distributed denial of service attack. And in this attack, an attacker will basically send a lot of requests to a target server, so many that it is overloaded and isn't able to respond. Now, my favorite case study to use is that of autonomous vehicles because there is so much machine learning going on. So autonomous vehicles lie on a spectrum of automation, where 0 is no automation and 5 is full automation. And somewhere in between there are things like driver assist. So most vehicles these days have some kind of driver assist technology. I've heard my car unfortunately does not, much as I love her. But common driver assist technologies include things like lane markers, or reverse parallel parking assistance. To be honest, I'm quite a good driver and I like showing off to people that I can do a really good reverse parallel park. So when the AI takes over, I don't know how I'm going to impress dates, but I'll do my best. A disruption attack on a computer vision system in an autonomous vehicle could prevent that vehicle from recognizing the lane marker or from being able to do a reverse parallel park very well. Now, in most jurisdictions, it's pretty common that a human is still required to, have both hands on the wheel, even if the car is driving automatically. So you can imagine that in this kind of attack, it would be pretty annoying, but not necessarily life-threatening. However, you can imagine a scenario where the car isn't able to recognize a stop sign and it does something entirely different. Or it stops performing at a moment when the human isn't paying attention and just doesn't have enough time to take over. Now, one of the reasons I like the autonomous vehicle case study is because there are so many different sensors feeding in data to enable a multitude of AI systems. So other data includes things like LiDAR, which is an RF-based signal that allows vehicles to interpret how close things in their environment might be. There's also things like GPS and Bluetooth. And so disruption attacks on all of these systems, maybe it doesn't sound so severe, but would cause massive brand reputation to these car manufacturers. We've seen examples of cyber attacks in the past leading to massive loss of trust in brands, like the Jeep Cherokee incidents, for example. Now, medical imaging is another good case study, both because my mum works in medical imaging and always sends me a lot of articles, which I really appreciate, so I know a bit more about medical imaging AI, but also because there is a vast array of different kinds of AI systems that could be used in medical imaging. So medical imaging is a field where different images from inside or outside the body are used to diagnose health conditions. These images could come in the form of ultrasounds, x-rays, CT scans, or even photographs. So this is a computer vision problem. It's also a signals classification problem in the sense that the reason that we look at these images is not because they were taken as images, but they came in as some other kind of electromagnetic signal. So ultrasound images, for example, use EM waves and are then converted to images later. So a machine learning system could also look at the signals that are coming in and make a prediction based on that. Adversarial attacks here can lead to false positives or false negatives, so detecting something that isn't actually present, or misdiagnosing or completely missing a condition. This is very distressing for patients. The interesting thing about thinking about the signal-based classifications is that it's a lot harder for humans to detect. I mean, depending on how well crafted adversarial perturbations in the computer vision space might be, at least it needs to pass the test that a human can't see it, or it shouldn't be easily detectable by humans. This is a much easier test to pass. Now, there's a lot of discussion around how AI systems could be used in the military, and much like considering AI use in healthcare and the medical fields, military and defence is also one where there must be a much higher burden on the organisation to make sure they do it right. Public trust is really important. The military has a different sort of license to operate. They need to maintain public trust to be able to perform. So one popular discussion around AI use in the military is around ISR, which stands for Intelligence, Surveillance and Reconnaissance, and in layman's terms basically says what are other forces doing and where and why. So you can see the appeal of being able to point a camera at a battlefield, and instead of having someone sit there around the clock to monitor what's going on, the AI system could just perform some kind of automatic detection to detect if there are humans or other platforms in the vicinity. This kind of system also extends to the RF space, where they would be tracking the RF signals emitted from other platforms in the sea, sky or land. These kinds of systems can be compromised by mitigations in the physical space like camouflage, or in the digital space through jamming techniques. Here's a funny example from a little while back. DARPA has been, as you know, designing and testing AI systems for exactly that use, for computer vision. Specifically, they're people detectors, so they should be able to identify when people are in the vicinity. They asked a group of Marines to try and hack these cameras, to try and get past the AI systems. And what they found was that it was actually really easy for the Marines to do this, and they did it by doing the funniest things. They put cardboard boxes on their heads, they held tree branches and walked around like a tree. They basically just acted like people wouldn't. And the reason that this worked was because the AI system had been trained on images of lots of people, and they were doing things that people would normally do. But by doing things that people wouldn't normally do, like putting cardboard boxes on their heads, the Marines were very effectively able to prevent the AI system from detecting them. This is a great example of a disruption-based attack because it stops the AI system from working, but it doesn't really require anything too high-tech. Another example of military AI use is a tool created by the US Navy called Threat Tracker, and it also uses machine learning to perform computer vision and RF-based machine learning to detect things in the vicinity. Now, I'll touch on the cybersecurity use case, noting that I'm going to dedicate another episode to AI for cybersecurity more specifically, and the ways that that can be attacked. So most machine learning systems in the cybersecurity space rely on some kind of signal data to be able to function. Anomaly detection is a really common use case for cybersecurity-based AI. Most of these techniques are akin to finding a needle in a haystack. So if the AI system even performs a little worse than usual, this can have quite a significant ramification on the probability that a threat actor is going to be discovered. I mean, the idea of disrupting algorithms in general has existed ever since spam filters have. However, as AI systems and technology has evolved, so too have the kinds of attacks that can be employed. Now let's talk deceive. So the same techniques that we can use to disrupt a model can often be used to deceive a model in a targeted way. The key difference here being targeted. So the way this manifests is usually in a classification or a prediction being forced by an adversary. So if we think back to autonomous vehicles, the disruption-based attack would be for the computer vision system of an autonomous vehicle to not recognize the stop sign. However, the deception-based attack is that the adversarial perturbations sent to the model, either in the physical or the digital environment, mean that instead of recognizing a stop sign, the AI system instead sees a 100 km/h speed sign. And this outcome has been predetermined by the adversary. This is actually pretty easy to do. What is hard is getting it into the physical world. And that's where a lot of these techniques really do suffer. For example, you'd have to basically replace the real stop sign with another one that you've crafted. Or you would have to find a way of feeding this signal digitally into the model. Now, this is definitely harder than just disrupting a model, but I would point out the amount of effort that criminals and adversaries go to disrupt cyber and information systems. They go to a lot of effort. So I'm inclined to think that one day they would go to the same amount of effort for an AI attack. And even if there's a possibility of that happening, we should ensure that our AI systems are robust enough to these kinds of attacks. Another interesting use case is facial recognition. Like the autonomous vehicle example, it's actually pretty easy to cause a model to misclassify one person's face, and this can be done using a variety of tactics. Some include changing the entire face. Some include adding some kind of adversarial region, so things like adversarial glasses, or maybe a hair accessory, or even makeup contouring. Another question I frequently get asked is, just because one company's AI system might be vulnerable to attacks like this, does that mean that everyone's AI systems are? For example, if you're a company that performs facial recognition, I use this example because I don't work with any facial recognition companies yet, and the question is, if another company's facial recognition models are hacked and disrupted or deceived, does that mean that mine could be too, or would they be safe? And this is a really great question, and the answer is you might not be safe. Most machine learning models are trained on similar kinds of data. So if you're a company that creates facial recognition models, firstly, how are you training your models? A lot of companies tend to use open source data repositories, which means that all of these machine learning systems are trained on the same data. If you're a company that's lucky enough to have your own data set, chances are it's still very similar to those open source data sets. The thing is, if you're training a machine learning system to do a particular task, regardless of what kinds of images you use or how you get them, models that perform the same task tend to what's known as converge. For example, the most common kind of model used for computer vision and therefore also facial recognition is the convolutional neural network. And now you can change a lot of things about a neural network by saying most neural networks tend to be 5 to 10 layers deep. They might use atom optimization or relu optimization. And for non-ML people out there, they're basically the ways that you can train the model. What the model is learning during the training process is the activations, weights, and biases. Basically a big matrix of numbers that are then applied to a new piece of data so that it funnels out a prediction or a classification. So you might have 10 different companies who are selling facial recognition models or software, and chances are the AI behind these systems are pretty similar. Maybe not entirely similar, like I'm not saying that they're still not proprietary, but they're similar enough that an attack crafted based on one target would be pretty good at attacking all of the others as well. Now, facial recognition is an interesting example because its use is increasing every day. It's used at banks, at airports, even at customer checkouts. Thinking about facial recognition from the lens of digital identity is a really interesting one because this is a big target for criminals and scammers to make a lot of money if they can impersonate other people by feeding fake identity information. These are particularly pertinent to price prediction models, risk assessment models, and fraud detection models. So adding targeted false transactions to a trading model could cause the model to exhibit subtle shifts, allowing the attacker to profit. Even small changes can lead to substantial financial benefits over time. Now, data poisoning and backdoors. This is when an attacker can add poisoned data in the training process or the fine-tuning process or the feedback loop of a model. This can manipulate the behavior of those resultant AI models and lead to compromised model performance in real-world applications. You've probably heard of backdoors in cybersecurity systems, but I bet you didn't know that they can also be employed in AI systems. Backdoors in AI refer to hidden vulnerabilities intentionally inserted during model development, which can be exploited by attackers to trigger specific behaviors or unauthorized access in the deployed system. Now, let's move on to disclosure-based attacks. These attacks cause the model to leak information it's not meant to, and it could be about the training data or the model itself. The terminology that's usually used here in cybersecurity and information security is exfiltration, often referred to just as exfil. Now we're finally going to talk about chatbots. You've probably heard of the ability to jailbreak chatbots. Large language models are the backbone of chatbots like ChatGPT by OpenAI and Bard by Google. Two models I use a lot to help me create my documents. Attacks on these systems can cause chatbots to give back dangerous or toxic content, and this is referred to as jailbreaking. Now, let's look at privacy leaks in AI systems. These involve the exploitation of vulnerabilities in AI systems to extract sensitive information or breach privacy through carefully crafted inputs designed to deceive the system. In the context of privacy leakage, an adversary could use membership inference to infer whether or not a particular person's data was used to train a machine learning model. These can have big ramifications for organisations where data and privacy leakage have massive fines attached. Now, it's also possible to steal a model. Model theft in AI occurs when adversaries illicitly gain unauthorised access to or replicate valuable machine learning models, potentially leading to intellectual property theft and misuse of proprietary algorithms and insights. AI systems are becoming increasingly valuable IP. I mean, imagine if GPT-4 was stolen. But even from a national security perspective, I mean, IP theft for engineering and cyber applications is a really big concern. IP theft of models or model information at the nation state level could have really serious ramifications. Now, maybe you're not convinced yet, and that's okay. Some of these may still seem a little theoretical to you. The point is that all of these techniques are methods that have been proven to work against models right now. Maybe most of the time now, they are in academic and controlled settings only. But I tell you, over the last 2 years that I've been working in AI security, the number of incidents that people will tell me about has exploded dramatically. When I started in this field in 2021, I was often the only AI security person talking at, cyber and infosec and hacker conferences, and it was a bit of a novelty. And this has changed dramatically over the last 2 years. This year, I was fortunate enough to go to what's referred to as Hacker Summer Camp in Las Vegas in August. And it is the trifecta of hacker conferences, B-Sides, Black Hat, and DEF CON. And at all of those events, I spoke to people who told me about real AI security incidents. Maybe it's not hitting the media yet, but it's about to, and it's going to be a groundswell when it does. There are already repositories for AI incidents. Some of these include the AI Incidents Database, the AI AAIC, have to check what that stands for. It stands for AI, Algorithmic and Automation Incidents and Controversies. Try saying that 10 times fast. And then there is also the AI Risk Database. And I do have to make the disclaimer that these events are a mixture of using AI for attacks and attacks on AI. But as much as I like to highlight the distinction, and it is an important distinction, I think, because the ways that you would mitigate these kinds of attacks are really different, but the ways that you would create these kinds of attacks are actually pretty similar. And so if we're seeing these techniques being used in the real world already for AI misuse, of course we're going to see them soon targeting AI systems. Okay, I hope this has given you a taste of the kinds of offensive techniques that are possible in the AI security landscape, and I've only touched on a few case studies. Every organization that creates ML models or uses someone else's ML models are vulnerable, and this really scares me. The thing is, there are lots of defenses that could be put in place, and different standards and regulations are starting to come down for AI systems, which makes me really happy. Things like security best practices, privacy controls, audits, assessments, logs. So the intention of this video isn't to scare you, but it is to highlight that these kinds of things are real, but ideally I want to leave you optimistic. That might not happen in this video, but by the end of this series, it absolutely will. So instead today we're going to move on as usual to the AI joke of the week. Apparently only a fraction of people make it to this point, so if that is you, please let me know in the comment, because I think the jokes are one of the best bits of these videos. Okay, here we go. Why was the computer cold? Because it left its windows open. Oh dear. So in the next episode, we're going to be diving into adversarial machine learning, and I'm going to be explaining the methods that power these attacks. Until then, please like, comment, and subscribe. It really helps my morale, and I'll see you in the next episode.